Welcome everyone. In this video we are going to derive a formula for the escape velocity. Escape velocity is defined as the minimum speed, the minimum velocity that an object needs to escape from the gravitational pull, gravitational attraction of another object. So let's say that we have a huge mass, capital M here, and we are on its surface. Maybe we are on the surface of the Earth. And I guess that is the case for most of us, probably all of us watching this video. And we fire a rocket upwards. Perhaps you're firing Voyager 1, a satellite, okay? And we don't want it to orbit the Earth, we want it to go to the infinity and beyond. We want it to escape from the Earth and explore the rest of the solar system, perhaps, okay? And it has a mass m. Now, if we throw it with a little speed, maybe if we give it a speed of 10 meters per second, it will come back to the Earth, right? And if we fire it with the speed of light, I know we can't, but if we do, of course it will escape Earth's pull. But I want to find the smallest amount, the minimum amount of speed that I should give it so that it escapes. And that speed I call the v escape, the escape velocity. Okay, now you might have heard the phrase what goes up must come down, and at the end you will see that that is not the case. And of course from the daily life we know that is not the case. We are able to throw rockets that do not need to come back to the Earth. So how can we find a formula for VE, the escape velocity? Well, I will consider two cases. The first case is going to be the initial case. It is starting from the surface of the planet, surface of the Earth for our case. And let's say that we have this point called F. Now, this point can be thought of as the point where we escape Earth's gravitational field. Of course, that is not possible. Gravitational fields extend all over the universe, but after some point you can neglect the gravitational pull of the Earth because there is an inverse square law, right? The formula that Newton gave us, the pull decreases with the square of the distance. So after some point we can neglect Earth's gravitational influence on our rocket. And that point I call F, the final point. Well, the conservation of energy tells us that the initial energy should equal the final energy. So energy is conserved. And in our case, we have two types of energy. We are dealing with mechanical energy. So we have the kinetic energy initial plus the potential energy initial. And this should equal the kinetic energy final plus the potential energy final. Now, since we are interested in the escape case, of course, we should take the potential energy final to zero. Because if it isn't equal to zero, then we still are being influenced by the Earth. So we didn't escape it yet. Okay, it should equal zero for our discussion. Then we have two terms left. I will also make another substitution, and this might be a little trickier than the last one. I also claim that the kinetic energy final should be equal to zero. And you might be saying, hold on a second, what does this mean? Why should my rocket stop when it reaches this point F? It doesn't necessarily need to stop, but remember, we define escape velocity as the minimum speed required. It is the minimum. It is the limit. It is the smallest energy that we need. It is the smallest velocity that we need to fire from the surface of the Earth. So if we think of the F as the point that we escape the Earth, we just need our rocket to barely get there. When it gets there, we are done, we escaped. So it doesn't need to have a huge velocity when it gets there. It can have a very tiny velocity when it gets there, and theoretically it can have a velocity of zero when it gets to the escape point, so that we find the actual minimal value. And the speed of zero means a kinetic energy of zero because it is the energy associated with your motion. And if there is no motion, there is no kinetic energy. Alright, I hope this part makes sense because after this it is fairly simple actually. If we say subtract the initial potential energy from both sides, we get K initial is equal to U initial, and now we substitute our values. The kinetic energy is in the form 1/2 mass velocity squared. Which mass are we interested in? Is it the capital M? No, it is the mass of our satellite, mass of our rocket. It is small case m. Then we have the velocity. It is going to be the initial velocity, which is going to be the escape velocity, because we made these two substitutions. We made the final potential energy 0, and we made the final kinetic energy 0. So we can call it V escape. Of course, it is squared. And this is equal to, well, in one of my previous videos, I derived the formula for gravitational potential energy. You can access that video from the cards right now. And using that result, I'm sorry, I was a little excited. And by the way, my mistake, there should be a negative sign here. Excuse me for it, right? We subtracted U initial from both sides. We have a negative U initial here. So we have the negative value. And if we substitute for gravitational potential energy, as I proved in one of my previous videos, it turns out that it is equal to negative G, the universal gravitation constant. This is not 9.81 meters per second. This is another constant times the mass of the Earth, in this case, times the other mass of the rocket, divided by the distance between them. Now, this is the initial case. So what is the distance between our object and the Earth? It is simply going to be the radius of the Earth. So it is going to be R. And if we can, well, let's do it like this. We have these become positives, minus minus gives you a plus, and m's cancel. What does this mean? This means that regardless of the mass of your rocket, you need the same escape velocity. Of course, we neglect air friction, but you won't be dealing with air friction for a long time. After you escape from the atmosphere, there will be no air resistance, and actually the other gravitational fields would be a lot bigger problem than the friction. There will be the moon, there will be the sun, other planets, so you would need to account for them even before accounting for friction, I guess, but it would complicate the problem a lot. So we are only dealing with an imaginary case of one planet and one object. So what I'm trying to say is it is a lot complicated than this in real life, of course. It is rocket science, right? It is super hard. No, don't be scared. So we have, if we solve for V escape, it is 2 times G times M divided by R, and we take the square root. And this is the formula for escape velocity. Now, substituting your values for G, M, and R, you can calculate the escape velocities from different planets. And in my next video, I plan to make the calculations for our world, the Earth. And I also want to point out that since Earth is not a perfect sphere, the R value changes from location to location, so there will be different R values we use in calculating the escape velocity. So the escape velocity you need will vary from point to point on the surface of the Earth. And enough said, this is it for this video. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.